Yeah, thank you for the introduction and thank you for inviting me to talk about this topic, which is a lot discussed. And we had a nice presentation about in silico, so now it's in vitro, showing that in the packaging area, there are a lot of room for alternative methods of toxicity testing. Now, just let me start this presentation by summarizing what we have to face as a problem when we try to assess the safety of packaging material. If you do a migration study and you analyze the migrate, you get a lot of peaks, and these peaks actually reflect different chemicals, a lot of chemicals. And these chemicals are either fully or only partially characterized, but you somehow know what they are. And you have a lot which are actually not characterized at all. So the migrate is actually a complex mixture. And with respect to safety, if you think about that, as a risk assessor I am, you would dream about having all the chemicals identified, quantified, and also characterized toxicologically speaking, in order to be able to calculate exposure and then to do risk assessment. But in reality, we know that it's not possible, first, and for many cases, it's actually not necessary. And but there is a big thing here is about selecting the chemicals on which you need prioritize the limited resources. And actually, the talk will be about whether there is a value to use bioassays in order to set priorities. Why not? We know actually that there are many in vitro toxicology tools. There are thousands of them. We know that some of these tools have been used for a long time in risk assessment, like genotoxicity testing, and there are like guidelines which are official for that. We know that in general, these tests have been designed for pure chemicals, but still they are quite a lot used and actually recommended or requested for complex mixture, like novel food, plant extract of medical devices. So why not using them for packaging material? And in packaging field, people are still very reluctant about using these tools, but there are some academic work on that, and which have been actually reviewed recently, and one of the review is actually from the Packaging Forum. You see that also politically it is a bit moving. So you have this report from the European Parliament that you can actually interpret as saying that they would like to have more biotesting and maybe more bioassay involved. And even here it's the scheme of the ILSI Europe document on safety assessment of NIAS, which is probably the most advanced process to assess safety of packaging material, where you have a lot of citation of bioassay, although they were not really convinced that they can be used. And I think the problem which is seen in packaging field is that there are a lot of reluctance of using that because they believe that the quality and the validation of these tests are not sufficient, that there are a lot of limitations, like for instance, you don't have metabolic activation in most of them, and the data interpretation is very difficult. So I will address some of these points, not all today, but before getting into this question, I would like to just give you a definition of what I mean by bioassay in the present talk. Actually, bioassay are cell culture-based assays, and I see two types of cell culture-based assay. The first one, and you can see that like in Tox 21, is really to use cell culture for hazard identification and hazard characterization, and it's actually to establish safe level of exposure in vitro and then to use that for risk assessment. That's the first things, and a lot of work is actually devoted to that. What I am talking about here is something a bit different. which is, I think, cell culture-based system which have been selectively and specifically designed in order to detect some properties of chemical which are of toxicological relevance. It's much more about biodetection, about exposure. You can, if you mix that with analytic, actually anchor that to classical risk assessment, so it's not so difficult to interpret the data. And something which is maybe the most powerful thing is that you can manage issues sometime early without having to assess. And very often it's much simpler than getting into big discussion like we had previously, for instance. Just what they are, I will just describe two tests that we are using. The first is the Calyx assay. So you have cells, they have been actually engineered to respond to endocrine active chemicals. So chemicals entering the cells, interacting with the receptors, and then moving to the nucleus, and then there is triggering the transcription of a protein that then you can measure easily. And you have different receptors available, and recently we have introduced the use of S9 fraction, which allow actually to deal with metabolism. You have here an example of how it looks like. So it's a migration studies in a plastic cup. You can see here what we call an agonist effect. So it's estrogenic, you see here. And we could actually show that this activity was actually mostly due to the presence of nonylphenol, which is a known estrogenic chemical, and there was a good concordance between the two. You can have also antagonist mode, meaning that you will not see chemicals which are mimicking hormone, but which will inhibit the activity of hormone. And here you see the nonylphenol here. It's actually reduced the activity of testosterone in this test. And you see here an anti-androgenic effect. Here you have something we have introduced recently, an analysis of the cytotoxicity, which show that actually you don't have any cytotoxicity, meaning that this activity is a real one and not due to toxicity. Another example we are using also, it's Bluescreen. Bluescreen has been engineered to respond to DNA damage. And it responds to different mechanisms of DNA damage. You have also the metabolic activation. You include the cytotoxicity test. It's very performant. You have here a typical response of that. Here you have an example of using this. It's an experimental coating. You have a migration, and then you concentrate the migrate, you transfer into DMSO, and you get the bioassay. You can see if we focus on sample 1 that there is a clear response, and you see that with 50% ethanol you actually don't have this response, so you can actually discriminate quite well. However, it's not easy to interpret this data. Why? Because first of all, we have not been able up to now to actually identify what is actually active in this. The relevance of the migration study we have done has been actually challenged. And if you do the same experiment with another test, which actually is different from a mechanistic perspective, like the Ames test, you don't actually get any effect. And now we are studying the sensitivity of these two tests to make sure that the mechanisms are actually involved are actually important, and it's not just a problem of different insensitivity. Now, I hope I have convinced you that there are tests, can be used, and they can be used with packaging material, migrate. Now, for what we should do that, and I will focus just on 2 examples. There are others, but the first one is about is illustrated in this example. It's about what we call safety by design. It is about testing early new product and see whether we can actually discriminate. And here at coating, you have 6 coating. Actually, there are only 5, but we have tested 6. You have here different bioassays, and you can see right away that some coatings are actually very active in most of this, and others are actually virtually not active. So you can actually discriminate, and even if you don't know what it means, you can act actually. I am sorry, it's a bit it's the other way around, but if you look at the chemistry, and here it's a GCMS, you can see that the one which are very low in activity are also the one which are very low in migration, which say that, and this one was very low and has been actually designed to have little migration, which means that a way to go with that is really to make sure that we design packaging for having low migration and low level of migration, which is much more, which make us much more confident in terms of safety. And secondly, in terms of assessing safety is obviously much easier. Now, for some of them, just we go into fractionation, just to illustrate that it's really not easy when you have, I would say, dirty packaging. Here you see it's LCMS. There are different fractions. We can find actually the activity in the different fraction, but we are quite far away of knowing what is actually responsible. But with some suppliers, we start to get the monomers, the additive, and some synthetic oligomers, and we try to be able to be a bit better in terms of characterizing that. But it's quite complicated, and I'm not sure that's the way forward. Something which is important is really to do that as early as possible. And here is an example of monomers which should be actually used as alternative to bisphenol A. So let's focus on the compound A. You can see that, for instance, this compound A is actually not estrogenic. Here you have BPA. But what you see in an antagonist assay for this compound is actually much more anti-androgenic than the BPA, which means that when you want to do safety by design, it's very important to be quite holistic on what you are doing and not just focus on one specific endpoint. Another application which is much more tricky, much more controversial, but I think it's very interesting to put it in a forum like that, is the following. It's actually the application of the application of bioassay in the frame of applying the TTC, the threshold of toxicological concern class 3, Kramer class 3, for priority setting for further work on NIAS, which are not chemically characterized. So it's to use the TTC for unknown. Very provocative, but I think quite promising. So the idea is when you have actually a chemical profile like that, the idea is, or the question is, could we actually put a kind of threshold here, saying that the effort in terms of identification and toxicology should be on the peaks which are higher than the threshold, and for the rest would be of lower priority. Obviously, in this frame, the application of the TTC Kramer class 3 has been actually proposed. But we all know that to apply the Kramer class 3, you need actually to satisfy a number of constraints. For instance, you should show that you don't have a strong acetylcholinesterase inhibitors. And maybe the most difficult one is actually to get some confidence that you will not have any genotoxic chemicals. But if you think about molecules which are unknown, how do you establish that there is no alert on the genotoxic alert, since you cannot see the structure? But obviously you are interested by alert because these alerts are associated with bioactivity. So you would feel actually it would be logical to use actually bioassay to exclude this type of activities. And if I keep on the genotox, which I think is the most tricky and the most difficult, this has been done up to now using different elements. The first one is about using the information on the material, on the composition, the manufacturing and all this, and suppliers should have a lot of this. Then you can make a lot of conclusion based on the type of analysis you do on the migrate, and also you can do targeted analysis. And now it is also proposed that you should also apply bioassays, and in particular genotoxicity assay. Now the big challenge of this is about sensitivity. So what do I mean by sensitivity? If you ask test providers whether the test is sensitive, will say yes, my test is very sensitive. Why? Because in general, the provider of tests, they actually define sensitivity actually something referring to the fact that the test is actually getting the true positive and not too many false negative. And this is what is defined. So you get actually in a situation where you don't miss too many positive. That's the definition. What I was discussing earlier is much more linked to something which is familiar to chemists. It's much more about limit of detection. And if you compare actually what you can detect in a mixture in terms of level of genotoxic chemicals with the kind of level we would like to see, we would like to be able to detect, we see that there is a big gap into that. So meaning that it's not very satisfactory yet. Actually, we try to increase to optimize the limit of detection of tests. We did that with several tests. This is an example with the Bluescreen. There are different chemicals here. Most of them are genotoxic, different mode of action. And you can see here that there are the factors between the optimized versus the standard test. And you see that actually you can optimize the test. And but it's not enormous. I mean, it's not a massive improvement. But yes, you can do that. And it's observed for the key mechanism. It depends on the type of assay. It depends also on the culture conditions and also on the substances. Now, it's clear that it's not sufficient, and we are not satisfied with that, and we need actually a breakthrough. By the way, we have also tested, for instance, acetylcholinesterase inhibition, and we get to a very similar situation where from a sensitivity limit of detection perspective is not very great. It's probably less of an issue with receptor-mediated effect. So, not very positive up to now, so what's the way forward? So for me, I mean, what we dream right now, and we actually will start using that next month, is to use high-performance thin-layer chromatography coupled to bioassays. So what do you do in this situation? You have here samples. You are actually separating the chemicals on a thin-layer chromatography, and then you conduct a bioassay on the thin layer. So you have actually here things which are quite interesting, because here probably you have a high concentration local, so you will actually increase sensitivity. And also you know where the reaction is occurring, so it's probably much easier then to do the analytics and to identify the chemicals which are actually active. And if you look, it's something which has a lot been used in other fields, like the water quality and even in food analysis. And just here an example, here it's nonyl phenol, and we could see that based on this paper, for instance, that they were order of magnitude better in terms of limit of detection than what we have in the regular bioassays. And something interesting is that there is 1 or 2 or 3 papers using genotoxicity assay, and we will get into that. And I hope that in 2 years we will bring you nice data on that. So bioassay, there a role for bioassay. I think yes, there is a role to prioritize structurally uncharacterized chemicals, and especially with the TTC class 3. I think it's also quite interesting to use to actually get to know the presence of chemicals which would have activity that we don't want, like endocrine activity or very high potency. There is this problem of sensitivity limit of detection, and we see that maybe, I hope, HPLC bioassay will be a kind of breakthrough in this area. So just to finish, if you look at all this business of packaging safety, a lot is driven by chemistry, and in chemical screening, like non-targeted chemical screening, you get peaks. And people have a lot of experience in getting peaks, and it's a lot accepted. And you look at chromatogram, and there are peaks, and we know that there are peaks, and it's normal because packaging material is just chemicals. Now we are getting into the biodetection. You don't get peaks, you get response. And we have much less experience. It's much less accepted. And we say, wow, what's happened here? But if you want to know what's going on, you need to understand the concern for the peaks and for actually the response. And you can have a response which is not a safety concern. You can have a peaks which is a safety concern. You can have a peaks which is not a safety concern. So in the end, you actually need to somehow group all this and identify what is important, quantify, and do a risk assessment. And I think to use bioassay and chemistry is probably the way forward to be able to focus the assessment where you need to focus. And with this, I just want to thank the multidisciplinary group working on that. And I would like to thank you for your attention.